What's up, everybody? Welcome to Cam School. Today we're going to be talking about Snell's Law. So basically, Snell's Law explains and quantifies what happens when light travels from one medium to another medium. For example, what happens to light when it travels from air into water, or what happens to light when it travels from water into another substance, such as a diamond. So to understand Snell's Law, we need to consider light and what it is. So normally, we understand light to be an electromagnetic wave, as shown here on the top. However, to make Snell's Law a lot easier, we consider light, in this case, as a ray from a source, as shown here on the bottom. It really simplifies things and makes calculations and visualizations a lot easier. So, to help us understand Snell's Law even more, here is a little example. Say we have a car going from asphalt to mud. Normally, the car is going to be faster on asphalt than it is going to be on mud, as we probably have seen in videos or seen others do while driving. So this car is going to be traveling along. And when this car reaches this border between asphalt and mud, this front right tire is going to be the first to contact the mud. When it does so, the rotation of this right tire is going to slow down. It's going to get a little bit slower than the other three tires. When that happens, the car is going to slightly turn and go off course. The same thing happens when light travels from one medium to another medium. Keep this example in mind when we're dealing with Snell's Law. So here we have two different mediums. We have air and we have water. Just like the car, light's going to be traveling along, and then it hits this border between air and water. When it hits this water, it's going to slow down. And the light is going to be slightly off course from its original direction. Because of this, there's two different angles, as shown here. We call this green angle, or the beginning direction or angle, the angle of incidence. We call this second angle, after traveling to the second medium, the angle of refraction. Refraction means change of direction. So, in this case, we see that the angles are different. Green is slightly bigger than the blue angle. Light, when it travels in air or in a vacuum, has a speed of c. We understand that speed to be 3.0 times 10 to the 8 meters per second. Super fast. When light travels to a different medium, it has a new speed, which we call v. So down here in the water, we have v. In the air, c. Two different speeds. When we divide c by v, we get n. And n stands for index of refraction. Basically, n describes mathematically the magnitude by which light in a vacuum slows down by traveling into another medium. Based on different information that we're given, we can either solve for v, if we have c and n, or, like we already talked about, if we have v, we can solve for the new medium's n. Here we have a table of really common n values for different substances. So for vacuum, it's 1 flat. For water, 1.33. Fluorite, 1.433, and so on. So here on the bottom, we have Snell's Law. Snell's Law gives us two pieces of really important information describing light when it travels from one medium to another. It tells us the indexes of refraction for the two different mediums, and it also tells us these two angles. It tells us the angle of incidence that the light hit the border, and then it tells us the angle of refraction after it travels past that border. Normally, when we solve problems dealing with Snell's Law, we're given three pieces of information and asked to solve for one. So here, in this video, we're going to practice that technique of using Snell's Law to solve one of those pieces of information. So we have pretty easy steps in solving such problems. First, we want to draw a perpendicular line to the border of two mediums as shown here. Second, we want to write the knowns and the info that we're given. Then, using Snell's Law, we can look and see which things we don't know, and then we can write out our unknowns. Then we'll set up our equation, and then we'll solve for the unknown that we don't know. So here we have a problem. It says if the angle of incidence is 32.8 degrees in this picture here, in this situation here, what is the refractive angle? So we learned that angle of incidence is theta 1, so we're given that. And it's asking for the refractive angle, which is theta 2. If we look up here, we have N2, and we have N1. So great, we have all our unknowns, or all our knowns. And we have the thing that we don't know, which is theta 2. So we can write out our knowns. N1 equals 1.00, and 2 equals 1.33. We also know the angle of incidence, theta 1, which is 32.8 degrees. We don't know our angle of refraction, which is question mark. Then we can write out our equation. Snell's Law. N1 sine theta 1 equals N2 sine theta 2. From here, it's really easy. We have our three knowns, we have our unknown, and we can manipulate to isolate the unknown. So we're just going to divide to move N2 over here. N1 sine theta 1 over N2 is equal to sine theta 2. Then, to isolate this angle from the sine, we're going to take the inverse sine of this side. So we're going to say sine inverse of N1 sine theta 1 over N2 will equal our refractive angle, or theta 2. Then we're going to simply plug and chug these numbers in. Super easy. Put them in the calculator and see what we get. So here we're going to rewrite with the numbers. Here's 1. This is sine 32.8 degrees. And put that over 1.33. And that will equal our sine, or our theta 2, or refractive angle, which is ultimately 24.04. 24.04 degrees. Very, very simple. If you follow those steps, then you can solve for that unknown. Now, I have a couple of tips when solving that'll make reasoning everything out a little bit easier. First, you want to ask yourself, is the ray being squished or is the ray opening up? You might think squished, what the heck? But let me explain. So here we have air and water again. We have our diagram showing this ray and how it changes course. When it goes from this medium to the second medium, it appears as though this light ray is being squished towards your perpendicular line. When the ray is being squished, when it goes from this first medium to the second medium, that is telling you that it's going from a faster speed to a slower speed. The ray is slowing down. The opposite occurs when you see the ray opening up. So if the ray were to go like this, and it's opening up this way, then we know that the ray is going from a slower speed to a faster speed. Super, super simple, but it can really help you to make sure that your reasoning and your answers are correct. Another thing is, when you're doing problems with Snell's Law, ask yourself, do the answers make sense? So let's consider Snell's Law one more time. N1 sine theta 1 equals N2 sine theta 2. We know that both of these sides obviously have to be equal to each other. We also know, given the previous problem, say that this N1 is 1 and N2 is 1.33. Those are our knowns. Then you have to solve and say you get an answer for theta 2. If both of these sides have to be equal, you can ask yourself, well, if my N1 here is 1, it's smaller, and my N2 is a little bit bigger, that means that this sine theta 1 has to be a little bit bigger, and this sine theta 2 is a little bit smaller. So, for these sides to be equal, then you have small n, 1, and big sine theta 1 will equal bigger n, small sine theta 2. And that should help you. It's a really, really easy way to ensure that your answers are correct. Now, really quickly, what are the applications of Snell's Law? When you manipulate your original Snell's Law equation, you can solve for this angle, which we call critical angle. And these critical angles are used in fiber optics. Really, really cool. Helps us to communicate, transfer information, and things like that. Basically, fiber optics uses this critical angle to transfer light and information really quickly. Critical angle basically says, what's the smallest angle that I can come to this border at and have light stay in that first medium? And basically, we can solve for this critical angle by saying sine theta 1, or sine inverse of your N2 over N1. And then that'll tell you what your critical angle needs to be. And basically that critical angle tells us, if we have a tube here that's supposed to transfer our information, our fiber optic cable, at what angle do we have to fire the light so that it can stay within this fiber optic cable? That's one really cool application of Snell's Law. But always remember, Snell's Law basically explains and quantifies what happens when light goes from one medium to another medium.